Good afternoon, everybody. My name is Mattias Widmark, and I'm a rendering programmer at EA, Electronic Arts in Stockholm. Just before I start, I've been asked to remind you to turn off the audio on your cell phone devices, so please do. When I made this talk, I decided to not do a breakdown of the entire system and describe all aspects of it. Instead, I decided to just select a few areas that I believe will be interesting for you and focus on these. The areas I will cover are these. I will start with scalability and workflows, two areas that are really important for an all-purpose game engine, like the Frostbite 2 engine that this train system is part of. I will then talk a bit about CPU and GPU performance, and in particular about our procedural virtual texture system, which is, well, we spent a lot of time on it anyway, so it's interesting in that aspect. I will then talk a bit about data streaming and our global prioritization algorithm behind it. And just as a final note, I will touch briefly on the actual train mesh. So not much about mesh generation today. But before I get started, I want you to know what I mean when I talk about the Frostbite train system, because it has some aspect that you might not think is included in a train system. Of course, we have a train mesh, and in our case, it's generated at runtime from a height field texture. Nothing strange there. We shade the mesh using an algorithm called shader splatting. This algorithm lets the artist take basically any shader they want and project it onto the train surface according to painted masks. So in this particular shot, you can see some side predicted cliff textures predicted here. We have spline and quad decals. Spline decals for roads and quad decals for manholes, things like that. We have a pretty advanced system for terrain decoration. And terrain decoration is just a means of automatically, and at runtime, scattering mesh instances on the train. In this particular shot, you almost don't see the ground because the decoration system is so high definition that it can deal with even the smallest bushes at pretty high density. Just another shot there, and another one. The terrain decoration is usually more important than the train surface itself. This is without decoration, and then if you add it, you get a much more lush picture, and it's the decoration that catches the eye. We have a distraction system that allows you to modify the height field itself, but also to change the rendering of the train surface. Like that. And finally, we have probably the most or the least ambitious water system in any modern engine, to be honest. The water in Frostbite engine is just train decals, basically roads that are desnapped from the ground. Much of this talk will be about the various rasters and how we deal with them in the engine. So I thought I'd just enumerate them all for you. We have, of course, the height field. We have the masks used for the shaded splatting algorithm. We have a color map that artists can use to tint the terrain in a global fashion. We have physics material and destruction depth. There is also an albedo map for bounce light. And finally, some additional mask channels that you can use arbitrarily in your shader if you want to, for instance, do more classical texture splatting within the engine. So back to the actual schedule here. Start talking about scalability. Before talking about it, I just want to define what I mean with scalability. It's a pretty vague word. So with scalability comes arbitrary view distance, in this case between just a tiny distance, which you have if you're crawling on the ground in Battlefield 3, up to, say, 30 kilometers, which you can see if you're in a jet. The level of detail has to go very high as well. Again, when you're crawling on the ground, you still want the terrain to look sharp and crisp. We also have to support, again, arbitrary, very high velocities, since we are also doing racing games on the engine, like Need for Speed Run, where you can have a bumper cam and going really fast across the terrain. The main observation about scalability, and perhaps of this entire talk, is that it's all about hierarchies. If you are consistently using hierarchies in the engine, I'd say that you'll get scalability for free. Hierarchies are not new to terrain rendering, and almost all terrain engines have some sort of hierarchies built into them. But our engine is perhaps more on the flight simulator side of the scale than on the games engine side, meaning that everything is hierarchy, which you will see in this talk. The hierarchy in question is, of course, a quad tree. It's very natural for terrain. But I'll assume that you know all about quad trees, so I'll just jump straight into some specific uses that we have of quad trees in Frostbite. The most central concept here is the node payload. The node payload is nothing strange. If you have a node in the quad tree, you can attribute it with a payload. It's basically a data blob. And the data can be a tile of raster data. It can be an instance array for mesh scattering, or a chopped up piece of terrain decal mesh. All the nodes have payload. Otherwise, there is no point with them. But normally, only a fraction of them have the payload loaded. So those payloads are actually in constant motion. They're being streamed in from disk, they're being procedurally generated, or they're being freed and removed. And this happens every frame. There is a prioritization mechanism to control all of this, and I will get back to that later in the presentation. When you have a quad tree, it's quite common to have the payloads or the data at the leaf level. In the Frostbite engine, we have data on all levels in the quad tree. The inner data, which is orange in this picture, represents LOD. The closer the data is to the root node, the lower LOD it represents. So I'll try to explain the big benefit of having the LOD payloads. But first I want to show that the payload usage is view dependent. In this case, we have an observer somewhere on the terrain, and he needs those green blobs or payloads to render that particular view. If the observer moves, he'll need another set of payloads. Now, the motivation behind the payloads. If we have them, we can actually make the terrain almost arbitrarily big without running into issues with the number of payloads needed to render the scene. That is to say, the number of green blobs here does not depend really on terrain size. The Frostbite engine would easily scale up to the entire Earth without running into problems. If we didn't have the LOD payloads, we would be forced to put all the data at the leaf level, and that does not scale. If you make the terrain twice as big, you will have twice as much data items to deal with and twice as much overhead. The LOD payloads are completely hidden from the user of the system. The user only works at the leaf level, so all the source data is at leaf level, and the LODs are generated and added at pipeline time. We have to deal with a few requirements when we generate those LODs. For instance, we have to add some borders. Borders are needed for the rendering algorithms when we're using filter kernels that are bigger than 1 pixel. We also need to make sure that we have continuity between all the payloads or all the raster tiles. If, in this case, we want to generate the green area, the green raster tile in the pipeline, we have to look at a few child tiles, the red ones, and resample those. But we also have to consider all the neighbor tiles to make sure that we get continuity across the borders. It's nothing strange, but you have to be really careful, especially with the height field raster, to avoid introducing cracks when you have those LOD payloads to deal with. As I said, the system is consistently using quad trees, so it's not only for the height field, it's also for the terrain decoration. And the terrain decoration payload is just a list of instance transforms. Those transforms are generated at runtime. The algorithm takes as input a set of rules, including density and scale factors and stuff like that. It takes masks that the artist has painted, and it takes the height field. And the algorithm actually runs across both GPUs and SPUs and CPU. And when it's finished, it has taken all this input and generated a local list of instance transforms for that particular area. To complicate things a bit, we also have LOD payloads for mesh scattering or terrain decoration. And that's actually a bit non-standard. I haven't seen it myself in any other engine. So it might be a bit confusing, but I'll try to explain. In this case, for decoration, we used LOD payloads again to achieve scalability. If the payload is close to the root of the quad tree, it represents high view distance. If it's close to the leaf, it represents high density. When rendering the decoration, we add the payloads, which means that you can achieve high view distance and high density for the tree or the bush or whatever you are decorating the terrain with. That's a bit abstract, perhaps. So here is a sequence of figures, screenshots to try to explain this. At the distance, let's say that this is at quad tree level n, we have some trees scattered. They're far away, but pretty low density. Closer by, the density increases because we add a payload at the next quad tree level. Zooming even closer, we add level n+2 here, containing some bushes. Now we're down to n+3, and we have added some leaves into the terrain decoration. And finally, really close to the ground, we are at level n+4, where we have added more leaves to get the density up, as well as a bunch of branches. So that's what I wanted to mention now about scalability. I'll get back to it later. Something about the workflows. Workflows are really important to an engine like Frostbite, which is used by many game teams. So we spent quite a lot of effort on it. The editor for the Frostbite engine is called Frosted. And inside this editor, there is a level editor, of course, but there is also something that we call the game view. And that's just the game rendering running inside the editor. The editor can look like this if you are editing a terrain. So on the left-hand side, you see all the terrain layers. The terrain layers are used both for shader splatting, but also for the terrain decoration. You can also see the height field and the physics materials and other rasters that I've mentioned. On the right-hand side, you see brush settings and some properties of the selected layer. You can click the little game view button to get the game rendering up and running. The thing with the train is that we support all train editing inside this game view. So it's really what you see is what you get in the interface. You can sculpt the height field, you can paint masks, or you can scatter the decoration, or move around the roads. Everything works inside the game. If that's not enough, we also support exporting all layers of the train, or any layer of the train, either the entire layer or select area. We also export a metadata file so that once you're finished editing the train inside your external editor, you can re-import it into the right position automatically. So those workflows are pretty good if you ask our artists, but they're not perfect. So a few issues. One is the conflict between wanting to optimize the data and wanting to change that real time. So what actually happens is if you try to sculpt the height field, you'll get a stall. That's when you have your coffee. And when the pipeline has finished rebuilding the train without optimizations, you can start actually edit it. Another issue that's common with the Frostbite engine that we are really trying to attack now is that the real-time editing path is different from the pipeline path, which means that you basically have two data paths to maintain when you support real-time editing in the engine. If you have a very procedural system like the train system, and you edit various aspects of it, you have to be a bit clever to make sure that the procedural content is regenerated. In our case, that when we added real-time editing, this was already done because we already supported destruction. And destruction had the ability to just go into the procedural train anywhere and just change it around. What we have discovered when making this scalable tool is that we are surpassing the limits of many popular third-party tools like GeoControl and World Machine. You can easily make a 64K raster, train raster in Frosted. But if you would try to roll that in World Machine, you'll run into problems. There's no real solution for that. It's just waiting for those tools to catch up, I guess. Something about CPU and GPU performance. The CPU performance started out pretty bad when we made a train system in the beginning. It could easily consume 10 milliseconds of PPU time just to bookkeep all of those quad trees. But we took all the work, we put it into jobs, we went wide whenever possible, and inserted the jobs into the general job graph of Frostbite. And at the end, we usually use 1 to 2 milliseconds SPU time and less than 1 millisecond PPU time for the train in Battlefield 3. And then about the GPU. We have two major optimizations for the GPU. The first one is that we analyze the train in the pipeline, and we figure out what permutations of terrain layers that will be splatted and pre-generate the shaders for that. The other big optimization is the procedural virtual texturing, which I will get back to in just a bit. With those optimizations, we're able to render the train full screen into the debug from PS3 in 2.5 to 3 milliseconds, which is lying a bit because that train will be a bit blurry. We have a detail overlay system as well. So when that is added, the cost goes up to maybe 7 milliseconds in difficult cases. I'll talk more about that detail overlay later. The terrain decoration can be arbitrarily expensive because it's procedural. It's just for the artist to put in a high-density figure and then you completely blow all the budgets. But usually on the Battlefield level, it's between 1 to 4 milliseconds. And also for the virtual texture, we have to maintain the tiles and regenerate them, and that costs between 0.2 and 0.5 milliseconds. I've been mentioning this virtual texture a few times So what is it? Well, before telling you what it is, I'll tell you why we have it. And the shader splatting algorithm allows the artist to make beautiful terrains, but they can easily become very expensive. We've seen figures like 20 milliseconds on terrains, which is completely unacceptable. Another thing with shader splatting is that it doesn't scale with view distance. The higher view distance you have, the bigger the triangles or the primitives, and the harder it will be to generate those shader permutations because you'll bring in more and more terrain layers. And eventually, at a certain distance, it just breaks down. The shader permutations become too complex. So, with those problems, we decided to try out the virtual texture approach. The virtual texture is basically shader splatting into a texture. And doing that, we leverage the frame coherency quite well, which gives us performance. But we can also afford to do multipass rendering if needed. So it actually gives us scalability as well. And as I mentioned, once you have the texture, you can just lay it down into the debuffer, and it takes 2.5 to 3 milliseconds. I will assume that you know about virtual texturing. If you don't, there are many presentations and papers to read about that. So I'll just iterate on the figures that we used in our implementation. So the virtual texture is 32 samples per meter. It's not entirely sharp. We have 256 tiles with borders, but the borders are integrated. We use an Atlas storage with the default size 2x4K for those tiles. We have to put 4 channels in them. It's basically like a small G buffer. And therefore, we have to have 2 textures. And the textures are DXT5 compressed. Finally, perhaps the figure that's a bit surprising, and that's the resolution of the virtual texture. It can become very large, like 1 million times 1 million pixels, which is 1 terapixel. Well, that's pretty large for a virtual texture. When you do virtual texture, you have to have an indirection texture as well, at least when you implement it with software. Hardware is coming, but it wasn't available when we made this engine. So we have an RGBA8 texture storing the indices and the scale factor. That's standard. We also have a continuous LOD factor, and we use this factor to fade in newly generated LODs. So someone pointed out that we should try to launch the word teratexture as opposed to the already existing megatexture. But I'm putting it inside quotation marks because it's really not that cool as it sounds. But we do have these large textures. And how do we do them? If you do them with classical virtual texture, you have an indirection texture that's some 4K by 4K, which is not working at all. It's way too large. So what we have done is that we use a clip map for the indirection texture itself. And the clip map is actually an old SGI version of virtual texturing. They even had hardware support for it in like 20 years ago or something. By using the clip map, we are able to reduce the 4K indirection texture into 6 64 by 64 clip map layers. The reason why it's not as cool as it sounds is that we resolve the clip map on the CPU for each draw call. So basically what we have is that we have a stack of classical virtual textures on top of each other. We just select one with appropriate resolution for this particular draw call. We could resolve this in the pixel shader, but that would be an additional cost that we decided to not take. For this to work, we have to have a pretty good alignment between texture space and world space, which is not an issue for terrain, but if you're trying to do a generic virtual texture system with those Terra textures and apply it to all meshes on a level, you're probably better off just having a set of ordinary classical virtual textures. Another thing we do with our virtual texture is that we generate it on the fly at runtime. We composite the tiles on the GPU, and then we pass the data on to either the GPU or the SPU, depending on platform, to compress it into DXT5. And by compositing the tiles at runtime, we have some benefits compared to streaming them from disk. Of course, we don't get a very large disk footprint. Instead, we have some data magnification of about 1,000x if you compare the virtual texture size with the sizes of the source rasters. The latency is lower because we don't have to do a round trip to the disk. We can just ask the GPU to composite the tile, and it will be read in the next frame. We can do dynamic updates on this virtual texture. It comes natural, which is a requirement for the engine because we need support destruction. We need to change the texture to be black, for instance, where there's an explosion. And finally, we don't request artists to paint the terrain down to every single pebble, so they won't have that full control. But on the other hand, they can work with much lower resolution source data. Again, as always with rendering, it's compromises. So there are issues with the virtual texture approach. It does solve the performance problem that we set out to solve, which is a good thing, of course, but it has some drawbacks. One is, or perhaps the biggest one, is the blurriness. On the console, we don't have really the memory budget to have full, sharp virtual texture, so it will be slightly blurry, the terrain. The texture compression, DXT5 has quality issues, and if you compress it at runtime, it's even worse, because you have to trade quality for speed. The cost of maintaining the virtual texture offsets some of the gain, but not nearly all of them, so it's under control there. One thing with virtual texture is that there is no hardware support for them. So anyone trying to work with them has seen that you have to either do filtering quite manually in the shader or just turn off some of the filters that you normally have on, like trilinear. We don't do trilinear on consoles with the terrain in Frostbite. It's just too expensive to do it in the shader explicitly. And finally, even if we do compositing on the GPU, there's still latency, especially because we're throttling. We can't do more than one tile every frame. And if the observer moves very fast, we need more than one tile to make the view sharp. So there will be some latency in the system. Final issue with the virtual texture. I mentioned that it has 32 samples per meter, and that looks pretty bad if you're going to crawl on the ground. We need something like 1,000 samples per meter. To go up to that resolution, we re-added shader splatting. So we now have detailed shader splatting as well. This means we have two shader splatting methods. And when you author a shader for terrain in the engine, you have to define both diffuse, normal, what have you, but also direct diffuse and direct normal. The first outputs, they go to the virtual texture, and the second set of outputs there, they go to the detailed splatting. Now, the main reason for having the virtual texture is that shader splatting is too expensive, or very expensive at least. And now we're adding it again, so But the good thing is that it's only for the details. So we can limit the view distance, typically to 50 to 100 meters, and then the cost of this detail shaded splatting is kept under control, often. I will now talk a bit about the streaming solution that we have to get the memory footprint down. In the previous version of Frostbite used in Battlefield Bad Company games, for example, we didn't stream the train because we didn't have a need to. But now the requirements have changed and the levels are bigger, and we're also doing the Need for Speed games, which actually have even bigger levels than Battlefield 3. So we had to do something with streaming here. The unit or atom that we stream in and out is a tile of raster data. For height field, it's typically 133 tile. For mask, it's 66, and color, 264. So they all have borders. And that's the data that we're streaming from disk. We're streaming them into fixed size pools in the runtime, and those pools don't depend on the train size. So no matter how big train you have on disk, you won't affect the memory footprint of the runtime. In the engine, we have, since it's a general purpose engine, we have many ways to stream stuff. The easiest one is tile by tile streaming. It works well for slow gameplay when there are not that many new tiles that you need to load every frame. We have bundle streaming, where we put a bunch of tiles together according to some rule and stream them with just one seek on the disk. And then we have hybrid streaming, which is most common. Then we use both bundles to load the basic resolution and then add resolution using free streaming. Those bundles are defined using what we call train resolution layouts. Here we see the source data layout for a level. And you can actually, the tiles, the leaf tiles or the chord trees here. You can see that the designer is able to concentrate the resolution in an area of the level so that they don't have to design full resolution in the surroundings where the player will never go. So that's quite convenient. Now, if you want to stream just a part of it in a bundle, you define a train resolution layout that can look something like this. So the user is spawning into the level, and then as they progress, we load a series of these train tile bundles. The thing with streaming is, especially with all streaming, is you don't get down to zero memory. You just reduce memory. You still have to have a resident set loaded. And we did some math on the resident set need for a train. And we found out that if you want full sharpness, you would have to spend some 70 megabytes. This is with streaming. That is way too much. So we had to do something. Then we came up with a feature that's called blurriness. The name speaks for itself, I guess. It's an integer, starts at 0. If you increase it by one value, you save some 70% of memory by blurring the train. This is proven to be very important for BF3 to get down from the 70 plus megabytes to 32 megabytes that we ship most levels with. Blurriness is just a generic word. What it actually is MIP bias applied to train streaming, or to train raster streaming. So if you have blurriness 0, you stream the train tiles all the way down to full sharpness, so that the texel in the train raster data, say the height field, covers roughly 1 pixel on screen. If you have blurriness 1, you stream, but you stop when a texel covers 2 by 2 pixels, and so on. We implemented the blurriness by a trick in the pipeline. So for each level of blurriness that the user wants, we cut the tiles in half, and we add one leaf level. We're not losing any data when we do this. We're just shifting it downwards in the quad tree, making the quad tree deeper, and thus the data is loaded in later. Small figure here to try to explain it a bit better. If you have blurriness 0 in this case, you have a set of 8 resident tiles to render a specific view. If we go blurriness 1, we have to add a leaf level. That's the green node, 14 new nodes added. But at the same time, we have cut the tile size into half. So it's 128 instead of 256. The resident set doesn't grow that much. In this case, we just add 2 tiles to it. But since the tiles are much smaller, we still save 68% of memory. Of course, blurriness is not good. You don't want to blur a game. So what we did to try to get around that and still have a game that looks kind of sharp is we blurred only the expensive rasters. The height field is 2 bytes per sample, and the mask is 1 byte per sample, so we blurred those. But we keep the color raster because it's DXT1, so it's cheaper. And then we make sure to put some high frequency detail into the color map to hide the blurry height field and masks behind it. Final note on... no, that's not a final note, but a funny note at least. When you're streaming height field, you have a pretty big risk of ruining the physics. So if you're not careful, you can get stuff like this. This is from a bug report on an early version of Battlefield 3. And it's actually the reporter that put the arrow in there. I think it's a bit funny. Spot the problem. In this case, the Jeep spawned before the train was streamed in. We have settings to avoid this. I won't go into how they work, but if you don't use those settings properly, you get artifacts like this. Now, when you're streaming, one of the big issues is the disk seek time. And we want to reduce, not the seek time, we can't do anything about it, or well, we can, but we want to start by reducing the number of seeks. We have several attacks on this problem. The first one is, the most important one is the train resolution layout, so that we can bundle a bunch of tiles into a big chunk, which we read with just one seek. If we don't do that, it can take minutes to load a level, literally, or at least 1 minute. That's not very good. We also co-locate tiles of different type, but covering the same area on disk. So if you have a height field tile overlapping a color tile, we take those two together and put them in one bundle and read them with one seek. We also have a way to co-locate nearby tiles. So we just make small clusters of tiles and store them together. In this case, the red nodes, the leaf nodes, can be bundled together and put as what we call a second LOD in the parent or ancestor node. To load the quad tree now, it takes, in this case, 10 seeks instead of 13. So it's normally 20 to 50% gained by doing this. You could imagine that we make bigger bundles, include more nodes, but if we start doing that, we waste quite a lot of memory by including nodes that we don't really need. So we shipped with just one level of bundling like this. Seek time is bad. Throughput can be pretty bad as well. To deal with that, we compress the data in pipeline. Color tiles are compressed, as I mentioned. We compress mask data by chopping up into pretty small tiles, 66 by 66, culling away the black tiles and merging the white tiles, which is surprisingly efficient, actually, just doing that. The physics and destruction depth, we compact those in 4-bit with run length encoding, and then everything is compressed once more. So that improves throughput a bit. Another thing that improves throughput is that we support incomplete quad tree. Normally, you have 0 or 4 children in a quad tree. But by allowing any number of children loaded, we can shave off some 20% of the nodes needed, improving the throughput a bit. Even if we do all this, there is still a significant amount of latency in the system, and at a certain point you can't just get rid of it, so then we have to try to hide it. And the two main methods we have of hiding the latency is to use continuous LOD whenever possible, so that at least things don't pop in when it comes in late. And we also have a global prioritization scheme, which I will talk about just now. And this scheme helps to distribute the punishment, so that not the local area of the train goes blurry when streaming is not keeping up, but the entire train goes slightly blurry. So this global prioritization. It is an algorithm that goes through all the nodes every frame and compute the priority value for them. We then update streaming, virtual texturing, and the train decoration systems according to those priority values every frame. Priority value is just a float. If it's 1.0, we are on target. That's what we want to be. If priority is lower than 1, then it's a low priority node. We don't really need data for that node. But if priority is higher, we need the data. The priority depends on distance and node size. If a node is closer to the observer, it will have higher priority. So it's red in this picture. But also, if a node is larger, it will have higher priority. This is basically a screen space projection prioritization scheme that we have here. We then modify the priority according to several modifiers. So in normal, this priority would be 1 for this node. If the node is in motion, it gets lower priority. This is something we added in just the last week before shipping Need for Speed Run, because we had discovered that if you drive really fast for a few miles along the track, the train just gets more and more blurry. And we found out that this is because the frame-to-frame accuracy is too low. So we spend all the throttled channels, the update channels, on the train just below your car, just in front of it. And we don't have enough resources to update the train around you. To solve that, we just lower the priority for nodes that are in motion. It's actually not the node that's in motion, it's the observer, of course. If there is an update like a crater, we boost the priority a lot to have it updated soon. On the other hand, if the node is occluded, we lower the priority. And the same thing is if the node is outside the frostum. Note that we just lower the priority. We don't cull away or skip this entire node. So if the occluder suddenly disappears, you would still have the train behind it. It's just a bit blurrier than it is around it. The update algorithm based on those priority works like this. You have all your nodes, and some of them with the payload. High priority nodes have the payload, not low priority ones. We strive to keep the pool size, the pool full, even if we don't need to. That works like a pretty good prefetch algorithm. So this is frame 0, it's a steady state, this is where we want it. Frame 1, the observer moves, and there's a shuffle in the priority list. We then run bidirectional search on this sorted list, look for nodes that need payload and nodes that shouldn't have. We identify the node that shouldn't have a payload, offload it, and the next frame we'll be able to fill the new hole in the pool with the new data. This global algorithm is really robust because it's touching all the data and all the nodes every frame. It does cost some time to do this, but after some optimizations, it's down to less than 1 millisecond on the SPU and less than half a millisecond on the PPU. You could time slice it if needed, but so far we haven't seen the need to do that. Okay, final little topic here is about the mesh itself. That's perhaps what your first thought is when you think about train system talk. But in Frostbite, to be really honest, the procedural mesh that we have is not really that much to talk about. It's very straightforward. But it can be good to know that you can ship a decent game using a straightforward algorithm. So the mesh we have is generated from the height field, as I mentioned. We tessellated using patches of 16 by 16 triangle pairs. There's only one patch that we move around for each draw call. We aim at using a level in the quad tree that's appropriate to get roughly constant screen space per active triangle size. Unfortunately, as you can see in this image, we're wasting quite a lot of triangles in the foreground here. It's pretty level with many triangles. And we have to take those triangles from somewhere, and that's from the rest of the train. So especially on consoles, our train mesh can look pretty blocky on the crest lines. On the other hand, all those triangles are kind of needed because we need support destruction everywhere. So at any time, there could be a crater added, and we need some triangles for that. On PC and Xenon, we sample the height field in the vertex shader. So we move around this patch, and we get the height for it in the vertex shader. On PS3, that's proven to be a bit too expensive. So instead, we are using a pixel shader to sample the height field for a 16 by 16 patch in advance and store the result in a vertex attribute array, which costs some memory, but it otherwise works pretty well. The stitching of the mesh or T-vertex removal is pretty straightforward as well. We have a job that runs through the quad tree and looks at all neighbors of each node that we're going to draw and look at what LOD they are on. And depending on the result of that traversal, we select what stitching permutation to use. And the stitching permutation is just an index array permutation. We don't touch the actual vertex data. To limit the amount of permutations needed, we are enforcing maximum one LOD skip on an edge. So you can only have one triangle to one triangle or one triangle to two triangles. Finally, we also have support for DX11 tessellation. It's pretty basic at the moment, but we are improving this a lot right now, and it will be quite much more advanced in a few months. So what we have is a height field. We use it as a displacement map. The good thing here is that we already use the height field as a normal map, so we have it loaded at pretty high resolution. So using tessellation here does not cost any more memory. The hull and domain shaders are schoolbook, straightforward examples. The tessellation factors are, for example, derived from screen space projection of the patch edges. So this is tessellation off, and this is on. It's not that big of a difference in a still shot like this. The big difference comes when you're moving. And the terrain with tessellation looks so much more stable. That's actually it. Some wrap up. So we have a pretty robust and competent train system in the engine, which is dealing with height field, train decoration, water. The system is pretty scalable. It's more like a flight simulator than perhaps a classical game train system. The workflows, we have given quite a lot of thought and energy put into them to make them quite good. And the runtime performance is, it's not stellar. As you saw, we have like 7 milliseconds rendering with the details on. That's in the worst case scenario with full screen terrain, but it's good enough. And some special thanks. Of course, the entire Frostbite team, but also contributions from the EA Black Box and the coder in Brad. Criterion has helped with both streaming and the train decoration. Tad, Matthew, and Richard. And I'd also like to thank Andrew Hamilton, who has made all those nice Alpine spring screenshots that you've seen in this presentation. They're not from the game, they are a new level that he's been working with. So he made some screenshots of that for me. So if you have any questions. Yes?
I have a question about the UV mapping. Do you support some custom UV mappings like on nearly vertical surfaces, or does it always go flat, let's say XY world position?
So the question is if we support custom UV mapping or if it's just flat. And the answer is yes, kind of. You can do side predicted textures. What you do then is that you bring in the world space position inside your train shader. Remember that you cannot use any train shader you want. And then just compute the UV mapping from that. But every UV mapping has to be computed in the shader. We don't support loading it from disk or pre-generating it or anything like that.
I wonder if you could comment on the vertex counts per frame or the number of draw calls per frame?
Sure. It depends very much on platform, of course. On the PS3, we have some, if I'm correct, it's some 100,000 vertices and some 100 draw calls. Out the top of my head, it's probably not entirely correct figures, but something, it's pretty low actually.
I was wondering, when you're enforcing the LOD, one LOD difference, is that part of your priority system?
No, it's part of the culling job actually. The culling job traverses the quad tree for rendering, and when it terminates in one traversal, one branch, it just makes sure that the neighbors don't terminate too early. They have to continue until at least one level above where it terminated.
How many quads are in your list that you're sorting and prioritizing in order to decide who gets paged out or streamed out and streamed in? Like, how large is that list?
It's about a few hundred, say 400.
Okay.
Yeah, when you mentioned that you could see jaggies on far away, crest lines and stuff, did you try like upping the priority of that detail to get it back, or was it?
Yeah, we observed those jaggies and tried a few tricks. One thing we noticed is that we could identify them and just subdivide a bit more. But since our patches are pretty big, they're 16 by 16 triangles, we noticed that we ended up just subdividing everything a bit extra. So it costs too much. Unfortunately.
What was the reason for the extra border, the border pixels on the tile streams?
For the height field in particular, it's because we are computing the normal in a pixel shader. So we need to have a kernel that's 3 by 3 pixels. To get that normal out. And we don't want to spill over in the neighbor tile because that would make the pixel shader much more expensive to be able to resolve where the neighbor tile is stored in the atlas.
With the priority system, did you have to introduce any hysteresis to keep it from sort of flipping back and forth between loading one thing and loading another as you move the camera around?
Yes. We spent some time just getting that right. So there is a small, like 2% margin there where we don't move. We have had quite a lot of bugs where things are just flickering. Because of the continuous LOD, you don't really spot it. But if you look at the performance graph, you can see that it's, for example, constantly regenerating a patch of mesh scattering, eating up a few milliseconds on your SPUs just for no good every frame. All right. Thank you very much.